Chapter 18 is called electrochemistry, and so we're going to go way back to the time we did redox reactions and talk about exchanging these electrons, because the flow of electrons will create the electricity and allow it to flow through, which is what scientists are trying to do. So let's just review redox real quick. Redox is short for reduction and oxidation, and make a note that you cannot have one without the other. So we can write the half reaction for reduction or for oxidation, but it's exactly that. It is a half reaction. It's not the whole reaction, because you can't lose electrons without somebody else gaining them. And remember, we talked about Leo the lion goes grr. So losing electrons is oxidation, the loss of electrons. When you lose electrons, the charge becomes more positive. So as something becomes oxidized, its charge is going to go up. Reduction is gaining electrons, and so the charge is going to become more negative. And that one makes more sense because the charge will go down, which sounds like the word reduce. And then it talks about agents here, but don't worry about those. Those were taken out of the AP exam, so you don't have to worry about the agents. But the whole point is that you are transferring electrons. So I'm going to review this before I go into detail about how electrochemistry happens. Let's just review a little bit about redox from another chapter. And the first thing you have to be able to do is label oxidation numbers, which is the charge that things tend to become. And on the periodic table in honors chemistry, you probably labeled them. So the alkali metals are +1, alkaline earth metals are +2, and in general, they tend to be the charges that are on the periodic table. But as you get closer to the middle of the periodic table, they're less certain. So P and N, phosphorus and nitrogen, they are not always going to be -3. Sometimes they're going to be +5, and sometimes they're just crazy charges. But the closer they are to the edges of the periodic table, the more likely they are to be that oxidation number. But here are some other rules that you should keep in mind. Elements in their free state have an oxidation number of 0. And that's really hard for students because it's kind of ingrained in their head to use those charges. What I mean by that is if we have like pure sodium and I just have Na in the reaction, that is not a +1 charge. To be +1, it would either be bonded to something or it would literally show the plus on there. But if it's just a regular element in its regular state with nothing on it, it's going to be 0. That also applies to Hofbrinkel elements. So F2 has an oxidation number of 0. Hydrogen is a good place to start because it is almost always +1. The exception is if it's with a metal. So if it was with sodium and it was like this, then hydrogen would actually be -1. Oxygen is almost always -2. The only peroxide that you'll ever see is this, but I have seen the AP exam ask about the oxidation number of oxygen in hydrogen peroxide. So H2O2, you need to know the oxygen's charge there is going to be -1. And then there's one other example, OF2, the charge for oxygen is +2, but those are the only exceptions that you need to know for oxygen. And then just keep in mind that for a compound, they need to add up to 0 unless it's a polyatomic ion, in which case it will add up to that charge. Let's do some examples. So we're going to balance a redox reaction in an acidic solution. The first thing you need to do is figure out what got reduced and oxidized by labeling charges on everything. So H has a +1 charge, so I know that's +1. The chromium and oxygen all need to add up to -2. So let's go ahead and label oxygen. -2 times 7 is -14. We want it to equal -2, so that means the chromiums have to add up to 12, because 12 plus -14 will give us -2. And so each chromium is going to be +6. Over here, let's go ahead and label hydrogen's probably +1, oxygen's -2. So what does that get us? We have now +6 minus 2 is +4. So each carbon here would be a -4. I'm sorry, not a -4. They need to add up to -4. So each one would be -2. Over here, chromium, it tells us is +3. Oxygen's probably -2. So that carbon's going to be +4. And we have -2 +1. All right, so now let's compare everything and see what changed. Hydrogen looks like it stayed +1 all the way across. Chromium went from +6 down to +3, so that got reduced. And carbon went from -2 up to +4, so that got oxidized. And again, you cannot have one without the other. So you will always have something that got reduced and something that got oxidized. So let's go ahead and start with the chromium. We've got Cr2O7, don't forget that -2. Is going to turn into chromium 3+. The first thing is to balance the number of atoms. So we have 2 chromiums on the left and only 1 on the right. So let's fix that. Then you need to do the difference in charge times the number of atoms to figure out how many electrons you have. So the difference in charge here, +6 to +3, is a difference of 3, and we have 2 atoms, so we're dealing with 6 electrons. And you're going to put it on the side with the higher charge because electrons always bring the charge down. And then the next thing is we need to fix oxygen. And remember, when you need to fix oxygen, you're going to add waters. So we have 7 oxygens on the left, so we're going to add 7 waters on the right. And then the last thing is to fix hydrogen, you add H+. So we're going to add 14 H pluses here. All right, and that was it for reduction. Let's do the oxidation now. First thing is to balance the number of atoms. We have 2 carbons on the left and only 1 on the right, so let's fix that. And then we're going to do the difference in charge. So carbon went from -2 up to +4. That's a difference of 6. And we have 2 carbons, so we need 12 electrons. And we're going to put them on the side with the higher charge. Then we're going to fix oxygen. So it looks like we have 1 oxygen on the left and we have 4 on the right. So we're going to add 3 waters over here. And now we have 6 hydrogens in the water, plus 5 more, plus 1 more is a total of 12. So we need 12 hydrogens on this side, 12 H pluses. And now we're ready to combine some things. So let's see what we can do. We can cross off these 12 H pluses and make this into 2. Oh, you know what? Before we do that, though, we need to fix the electrons. Sorry, let's go back and fix the electrons. So however many electrons you lose, you have to gain by the other reaction. So we are doing 6 electrons on the left for the blue reaction and 12 for the red. So we need to multiply that whole blue reaction by 2. And I'm just going to go ahead and change everything because otherwise I forget. So this becomes 12, 2 here, this becomes 4, and this becomes 14. Okay, now we're ready to cross things off. So we can cross off these 12 H pluses, and that leaves us with 16 here. Electrons will always cancel out. We have 3 waters here, and that will make this 11. And I think that's it. So now we're ready to rewrite the reaction. That looks like everything on the left of the arrows. And then on the right, we have chromium. Sorry, that's a plus sign. And CO2. And this is the balanced redox reaction in an acidic solution. If it says in a basic solution, you're going to do the same thing, except you have one more step at the very end. So I'm going to rewrite this reaction real quick. So the difference for a basic solution is that you can't have H plus in the reaction, and so you're going to add however many hydroxides you need to turn all of those into waters. But you can't just add hydroxide to one side without adding it to the other side as well. And then we can actually fix some of the waters, so now these 11 waters get canceled and this turns into a 5. So the final answer would have 5 waters on this side, and then the whole rest of the reaction would be complete. So that's in a basic solution. All right, so let me show you how this now applies to electrochemistry. So what you're going to have here is 2 different solutions that you can separate with a wire, and the wire allows electrons to flow through it. So the black sticks there are the electrodes. One of them is copper and one of them is zinc, and they are just pure solid metals that have an oxidation number of 0. And what you can do is to put them into a solution that has ions of the same element. So in this one we have copper 2+ ions, and in this one we have zinc 2+ ions floating around. And so what happens is that zinc is going to be reduced. And so zinc is going to go from 2+ to zinc solid. At the same time, copper solid is going to be oxidized. It's going to lose electrons to become 2+. So the copper stick I'll try to color it so you can see it. Let's just say this is a little green piece of copper right here. This solid copper is becoming 2+. So it is going to actually break off from the stick and go into the solution to be copper 2+. And in the process, it loses 2 electrons that it shoots through this wire right here. And they go past the voltmeter so you can measure the voltage, and they're going to go all the way over here to the zinc electrode, and this zinc, all the way down to here. And then this little zinc 2+ that's floating around is going to grab onto those electrons and stick onto the end of that stick right here. So the copper electrode is actually getting smaller as the copper atoms break off and become copper 2+. The zinc electrode is actually getting bigger because the zinc 2+ ions that are in the solution are gaining the electrons, which turns them into the solid, and they will stick onto the solid electrode. So both of these are happening at the same time, but we've got electrons flowing as they go from the copper over to the zinc side. And so, like I said, you can measure that flow. There's a couple more things, though. You can't just have a whole bunch of ions in the solution. That's really unstable. So you're going to have some kind of negative ion to match up with it. So let's just call it sulfate. So let's put some SO4 here and some SO4 2- here. It's a spectator ion, so it's not going to actually stick to them. It's just floating around in the solution. But notice that on the zinc side, we don't need as much SO4 2- to balance the zinc ions because they're becoming solid. They're not ions anymore once they gain the electrons. And on the copper side, we need more because as the copper pieces break off of that electrode and go into the solution, they become ions, and they need a negative ion to cancel them out to keep it as a neutral solution. And so what we have to have is what we call a salt bridge that allows those spectator ions to flow from the side where there's too many of them to the side where they're needed. And so the SO4 2- is going to flow through this salt bridge and into the copper solution. There's a couple more things. There's a lot of vocab with this chapter that you'll need to know. And two of the main ones are cathode and anode. So the cathode is the side of the reaction where the reduction is happening, and the anode is where the oxidation is happening. I just remember that easily because C is a consonant and R is a consonant, and O is a vowel and A is a vowel. So the anode starts with a vowel, so it's the oxidation one that also starts with a vowel. So that's just an easy way to remember it. They don't always put it on the left and right, so you can't memorize that the left side is one thing and the right side is the other because it's in 3 dimensions. You can flip it around. And I'm going to stop here, and I will continue the notes in the next video.